Hello everybody. In this video we'll be covering one of the sections in chapter 7 of our textbook entitled Chemical Reactions. In this video we're going to be discussing oxidation-reduction reactions. So oxidation-reduction reactions, or what we often abbreviate as redox reactions, occur when one chemical species loses one or more electrons to another. We say that the element that loses the electrons is oxidized, and the element that gains electrons is reduced. Okay, and I like this little graphic here called the electron oil rig. So it's like a little mnemonic for you. Oxidation is loss, oil. Reduction is gain. You can't have one without the other. If something gets oxidized, something else has to be reduced, and vice versa. In combustion, oxygen atoms are reduced and non-oxygen atoms in the other material are oxidized. So we're going to see that combustion reactions are a subset of oxidation-reduction reactions. So we've been working with a lot of reactions so far where metals react with nonmetals to form ionic compounds. But we never really thought about why that was true, right? That the metal loses electrons and becomes a cation. This is because it's undergoing oxidation. And the nonmetal gains electrons and becomes an anion. This is because it's undergoing reduction, right? We talked about which ionic species we would form, and we knew what charges they would take on, but we never really thought about the fact that there had to be a transfer of electrons in order for that to occur. So in redox reactions, that's where we're seeing that the electrons are transferred from the metal to the nonmetal. So let's take a look at a redox reaction example. We've known for a while now that when we add magnesium metal to chlorine gas, we're going to form magnesium chloride. We knew what this formula was going to be based on the charges that these two species want to have. But we never really considered what was happening again. So the magnesium metal in this case has become this cation, and it's given up 2 electrons. And each one of the chlorine atoms has taken on an electron to form that chloride anion. We need to have balance between these electrons, right? So that's why we need 2 chlorines to balance out each one of the magnesiums. And then we'll see that their charges also cancel out. These reactions here that I've written are what are known as half-cell reactions, where we're showing the transfer of electrons. So we know that combustion reactions are ones in which O2 gas is the reactant. Combustion reactions release a lot of energy. They're exothermic, meaning they release heat. Combustion reactions are a subclass of oxidation-reduction reactions, though. There is a transfer of electrons. So let's take a look at how that works. So if we have a magnesium solid that's going to react with oxygen in this case, we can break this down. So our magnesium still loses 2 electrons, but the oxygen is in a 2 negative state, meaning it took on those 2 electrons. So here's where we have this balance. We get 1 magnesium for every 1 oxygen that we're going to reduce. That's why when we have our diatomic species, we need 2 magnesium atoms. So in a combustion reaction, sometimes you don't actually have any metals. And it's not very obvious that there's actually being a charge, electrons transferred, because we're not forming any ions in this case. But I just want to point out that that is still true. The carbon atoms are still oxidized. They're going from this C-4 situation to a C+4 situation. But these ions don't actually exist, okay, because we're having molecular compounds now. But we can still talk about them. And the way that we do that is we define something known as oxidation numbers. Okay, they help us to see the electron transfer, but they don't indicate that there's actually any ions being formed. In this case, again, the oxygen atoms are always reduced, which is a hallmark of a combustion reaction. So let's talk about the things that are going to help us recognize a redox reaction. Any reaction where O2 is a reactant or a product is a redox reaction because it's a combustion reaction, and combustion reactions are all redox reactions, right? So any reaction between a metal and a non-metal, right, where we're going to form those ionic compounds is a redox reaction. And any reaction in general where electrons are transferred, okay? When a free element gets combined into a compound, it will either be oxidized or reduced, okay? So when we see these two coming together, there's an oxidation-reduction reaction happening. There's some kind of change in electrons that cause that to happen. Remember that the movement of electrons is what's driving all of our chemistry, because the protons stay the same on both of the atoms, okay? When a metal cation changes its state, it will either be oxidized if its charge is increased or reduced if its charge is decreased. Okay, so here's an example where we have copper 1 plus here, and then it's turned into copper 2 plus here. Whereas we had iron 3 plus here, and now it's iron 2 plus. So some metals can have different oxidation states, and that is, they're moving between them because of a transfer of electrons. Let's do a couple practice problems and see if we can decide whether each of the following reaction is a redox reaction. Let's take a look at this first one. Yes, it is, and it's indicated because we have a metal, aluminum, reacting with a non-metal, bromine. And this next one, this is not a redox reaction because it's one of our other groups here. It's a gas evolving reaction. So if you can identify it as one of the other types of reactions we've talked about, it's not a redox. This is a oxidation or redox reaction, and we know that because iron changed its oxidation state. Right here it's an ion, and then here it's a neutral species. Okay, so it went from a 3 plus state here to a neutral state here. And we know that this is a redox reaction simply because oxygen is one of our reactants.